All right, so welcome to my series of video statistics. And in this video, I'm going to teach on um, confidence interval and hypothesis testing for paired samples. And before we do that, I want to iterate something. Now, in the previous video, I taught on hypothesis testing and confidence interval for independent samples, okay? Now, I taught on for independent samples when the standard deviations are known. That's the first scenario. And then for independent samples, when the standard deviations are unknown, but they are equal, right? Now, we can have a third scenario where the standard deviations are unknown, but they are not equal. If that happens, your calculated T will be done using this formula, right? Your calculated T will be done using this formula. And then when you want to look at your critical T from the table, you use obviously the confidence level or the alpha level plus the degree of freedom. Now, in that instance, your degree of freedom now becomes this formula. So that one, the computing the T is easier because there's no pool standard deviation, but computing the degree of freedom becomes a little bit difficult. So note that we can have a situation where the population standard deviations are unknown and they are not equal. And that is how we are going to treat it. Now, for the purpose of test, whenever you are not sure on how to state hypothesis, okay, whenever you are not sure, the question is not clear as to whether it's a claim or whatever, to be safe, okay, to be safe, just say U1 minus U2 is equal to 0. Then alternative, U1 minus U2 is not equal to 0, okay? If you don't know with the direction, if the question doesn't give so much clue to know whether it is a standard or whether it is a status quo or a claim, when you are dealing with independent samples, by default, this should be your hypothesis. The null is that there's no difference between the first group and the second group. The alternative is that there is a difference between the first group and the second group. So it will always be two-tailed, all right? If you are not sure of the direction, or if the question is silent, state the hypothesis in this way, okay? All right. Now, in this video, I'm going to teach on paired samples. Now, paired samples are treated in a way different from independent samples. Paired samples are treated in a way which is different from independent samples. So when it comes to paired samples are samples that are selected in a way that one sample is matched with the values with the second sample for the purpose of controlling for extraneous factors. Remember, when I was teaching you independent samples, I said the groups are very different from each other. One group is different from the other group. When it comes to paired samples, it is the same group, okay? But then we are testing for extraneous factors. Let me give you an example. Let's say before a statistics quiz, you have not watched my series of videos on statistics. And then I gave you a quiz to write on statistics, but you have not watched my video, and I wrote down your scores. Then you watched my video, then I gave you the same test on statistics, then I wrote your scores. So it is the same group that you have taken the exams, but then I recorded your scores before and after when you watched my video. All right, so when it comes to pair samples, it is the same group, but maybe we are testing for extraneous factors. Let me give an example. Testing a new paint mix versus an old paint mix. So for instance, let's say you want to look at the beauty of your room. It's the same beauty, it's the same room. But maybe you used a certain paint mix to paint it. You realize, no, it's not beautiful. Then you use another paint mix to test it. All right. So it's the same room, but you are using two different paints to test the beauty. Another example is testing difference in gas mileage, comparing regular gas and premium gas. So here, if you want to test that, you have to use the same car, not two different cars. The same car, you use the regular gas to test the mileage that the car can go. Then you use the premium gas to test the same mileage. But it's the same car, okay? It is the same car, right? Another example could be that, let's say for money, let's say employees, normally they go on a training section. When you arrive on the training grounds, they will give you a questionnaire to fill on what they are going to train you on. Then after the training, they will give you the same questionnaire to fill. So it's the same group of people who went for the training, but then they are recording their scores before and after the training. So it's the same group, but we are testing for extraneous factors, which is the training that they went for, right? Okay. Now, when it comes to that, okay, when it comes to paired samples, the point estimate is the difference, which is sigma D1 over N. So keep this in mind. The point estimate for paired samples is this, sigma D1 over N. That is the point estimate for paired samples, sigma D1 over N. That is the point estimate for paired samples. Then the standard error for paired samples is, so standard error or the standard deviation, whichever way you want to call it. Standard error for paired samples is square root of sigma D1 minus D, the mean of D, sorry, squared all over N. Okay. So this is the standard error for paired samples. This is the standard error for paired samples. Now, when it comes to the confidence interval, remember, every confidence interval is a point estimate plus or minus, sorry. Let me make this correction. Sorry. Actually, this formula is the standard deviation, not the standard error. Okay, sorry about that. This formula is the standard deviation for paired samples. So the standard error actually for paired samples is the standard deviation, this one, the standard deviation you've computed divided by square root of N. Okay, this is the standard error for paired samples. A standard deviation divided by square root of N, but the standard deviation itself is also computed by this formula, right? The standard deviation itself is also computed by this formula. So when you are done, you now use it to come and compute the standard error. Now, when it comes to some paired samples, by default, it uses a T. Okay, so for paired samples, we do not make a distinction between Z and T. For paired samples, for some statistical reasons, by default, it uses T as its critical value, not Z. All right, for paired samples, by default, because of some statistical reasons, it uses T. Okay, it uses T for its critical value, not Z. All right. So by our generic formula of confidence interval, it is point estimate plus or minus the critical value times the standard error. So for paired samples, its point estimate is D, this one. This is the point estimate. Okay. This is the critical value, the T. And then SD over N is the standard error. And when it comes to paired samples, when we are reading the critical T from the table, the degree of freedom is N minus 1, not N minus 2. When it comes to paired samples, it's N minus 1. Okay, when it comes to pair samples, we want to read the degree of freedom from the table. I'm sorry, when we want to read the D from the table, we will need when we want to read the T from the table, you need a degree of freedom and then the alpha or the confidence level. So the degree of freedom when it comes to pair samples, the degree of freedom is n minus 1, all right? N minus 1. Okay. Now, if you want to compute the T yourself, because when it comes to hypothesis testing, we will need a computed T and then the critical T. So for the purpose of hypothesis testing, we want to compute the T for pair samples. Any computed T, as you already know, it is what? The point estimate minus population parameter divided by standard error. Okay. So the point estimate is the difference that you compute, the D bar. Then the population parameter will be the population difference. Then the standard error is standard deviation of the pair sample over root n, all right? So that's how we compute T for paired samples. So let's take an example. The example here says that suppose an independent test agency wishes to conduct a test to determine which name brand ink cartridges generate more colors on the average than the competing generic ink cartridges. The test is conducted using paired samples. This means that the same people will use both types of cartridges, and the pages printed in each case will be recorded. You see, the question didn't even say pair samples. The moment it says the same people will use both type of cartridges, it must click that it's not two different people. It's the same group of people. So it is paired samples. It is not independent samples. All right. It is not independent samples. Now the question says that we want to know whether the name brand will generate more printing than the generic brand, all right? Whether the named brand, so they want to test a claim, whether the named brand will generate more colors than the generic brand, okay? So this simply means that the average number of pages printed by the name brand, okay, is greater than, that's the claim, the claim. The name brand, the average number of pages is greater than the generic brand. In other words, for the named brand, if this one crosses, the name brand minus the generic brand should be greater than 0. All right. But normally when we are solving this, we actually want the formulas to look different from the independent samples. So here the minus this will be the difference. Okay, the difference. The difference. This minus this, we denote it by the difference between the two. So the average difference between the two should be greater than 0. And this is the claim, all right? So in terms of hypothesis, the alternative will be that the average difference between the two is greater than 0. Then the null hypothesis will be that the average difference between the two is greater than, is less than or equal to 0. So this will be our hypothesis. All right. Now, our null says that the difference should be less than or equal to 0. That's what our null hypothesis says. The difference should be less than or equal to 0. So if I draw my curve like this, the difference is equal to 0, but the null says it should be less than or equal to 0. So we are looking for here, there's the acceptance region, but we allow for a little more. So everything here will be the acceptance region. But when we cross that critical bound, then we reject. So how do we get our critical bound? We have to go and look for the critical T. Okay, we have to go and look for the critical T. How do we look for the critical T? How do we look for the critical T when it comes to paired samples? Okay, how do we look for critical T when it comes to the paired samples? So when it comes to paired samples, the critical T, we will need the confidence level, okay? And then we will need the degree of freedom. Now, if you look at this question, the alpha was 0.01. That means they are testing at 99% confidence because the alpha is 0.01. And it's one tail, right? It is one tail. And remember, because the sample size is 6, the confidence level 99%. Because the sample size is 6, the degree of freedom is 6 minus 1, which is what? 5. So the degree of freedom is 5. Okay. So we are going to read the degree of freedom of 5, confidence level of 99%. That means for only one tail, for only one of the tails, the alpha is 1% or 0.01. All right. Let's go to our T table. For only one of the tails, the alpha is 0.01. So this is it. And then the degree of freedom is 5. So we have, so it's 5. So where they meet, we have 3.365. Okay? 3.365. That is the critical T. So our critical T is 3.365. But we need to now get the computed T to make decision. So computed T is, if you remember, the sample difference minus the population difference all over standard deviation root n. All right. So we are going to work out all these figures and then fix them here. Okay. Now in the question, the number of users are 6, user 1, user 2, user 3, user 4. All right. Now, how do we get the average difference? The average difference is that you first of all find the difference itself. So the difference is that you subtract the pages produced by the name brand minus the gene. So this minus this, you get the difference for the first person. This minus this, you get the difference for the second person. This minus this, you get the difference for the third person. This minus this, you get the difference for the fourth person. This minus, you get the difference. Now, how do I get the average difference? The average difference. If this is the difference for each of the 6 people, the average difference will be 6 plus -4. So you add all the differences. Plus 45, plus 13, plus 16, plus -3. And they are 6, so divided by 6. So you are going to get 73/6, which is 12.17. So the average sample difference is 12.17. Okay. The average sample difference is 12.17. All right. And we need to now get the standard deviation of the differences. The standard deviation of the differences. Okay. So the standard deviation of the differences. Remember that the formula for the standard deviation of difference is square root of sigma di minus the average difference squared all over n. Okay. So the differences were 6, minus 4, 45, 13, 16, and minus 3. And then you remember the average is 6 plus minus 4 plus 45 plus 13 plus 16 plus minus 3 all over 6. This was the average, and the average was 12.17, right? Okay. Now let's find the standard deviation. The standard deviation says sigma, so summation of each of the di means each of the difference. So the first difference is 6 minus the average difference, which is what? 12.17. Okay, bracket close, squared. Plus, so that's the meaning of the sigma. The second difference is minus 4. So minus 4 minus the average difference, which will never change. So 12.17 squared. Plus, the third difference was 45. So we have 45 minus at the average difference, 12.17 squared. Plus the fourth difference was 13. So 13 minus 12.17 squared. Plus the fifth difference was 16. So 16 minus the average, which is 12.17 squared. Plus the last difference is minus 3. So minus 3 minus the average, 12.17 squared. Everything here over n, then everything we find square root. So let's do it step by step. When you do it one by one and you put them in the bracket and punch on your calculator, 6 into bracket 6 minus 12.17 squared, you get this figure. So this one is this figure here. The third one is this figure here. The fourth one is this figure here. The fifth one is this figure, and this is the sixth one. All right. So we are still going to do this step by step. So we're going to add everything and divide by 6, then we find the square root. Okay. So we're going to add everything and divide by 6, and we find the square root. So approximately, you should get something around 18.02. If you don't get this, I think probably it's because of the rounding error, all right? If you get somewhere around 16, 17, 18, 19, it's because of the rounding error. But you're supposed to get the standard deviation of approximately 18.02, all right? Okay, now let's go back to our T. We said our computed T is equal to the difference, the sample difference minus the population difference all over the standard deviation root n. The sample difference we had was 12.17, the average sample difference. Okay, the average was 12.17. All right. Now, based on our hypothesis, the difference is equal to 0, less than or equal to, so the equal to is part. All right. So that means that here it will be minus 0, like the same way we did for the independent sample. So always the population side will be 0, unless the question says otherwise. Divided by the standard deviation we found, that is 18.02, all over square root of the sample size. Sample size is 6. because there are 6 people who used it, all right? So our computed T, if you fix everything, our computed T will be 1.6543. Our computed T will be 1.6543, all right? Okay, now let's go to our drawing initially. So our computed T is less than this critical T. It's 1.6543, all right? So since it falls in the acceptance region, we accept, all right? So we accept the null hypothesis, but of course we use the word fail to reject. So we fail to reject the null hypothesis because, so please, if you have followed it up until now, anytime the calculated T is less than the critical T, we don't reject, we fail to reject. But if it is small, we reject. So that's how it will look like. Anytime the computed T, okay, anytime the computed T is less than the critical T, we fail to reject. And anytime the computed T is more than the critical T, we fail to reject. And this will even work for negatives. So when you get a negative question, all you need to do is that you need to find the absolute, ignore the negatives, and use it to comment. All right, use it to rate the decision. Because if you always want to draw, you will not finish. All right. Okay. So because the computed T is 1.6543 and it's less than the critical T of 3.365. All right. Okay. So this will bring us to the end of the video on hypothesis testing for paired samples. Now, in the next video, I'm going to teach on hypothesis testing for population proportion, all right? So in the next video, I'm going to teach on hypothesis testing for population proportion. So see you in the next video. Thank you and bye.